Welcome to this presentation on pretraining and embedding layer. Today, we will explore how pretrained embedding layers have become a common strategy in neural network training. We will examine foundational theory, review current research insights, and demonstrate practical implementation techniques. We will also discuss limitations, architectural patterns such as shared weight schemes, and transfer methods for adapting embeddings across different vocabularies and model scales. If you've experienced slow convergence when training from scratch or struggled to adapt representations to a specialized domain, pretrained embeddings offer transferable, semantically rich vector representations that can mitigate these challenges. Pretraining embedding layers is one approach to improve model design when end-to-end training from random initialization may be inefficient. In the case of language modeling, instead of starting with random embedding vectors and relying on downstream supervision to learn semantic structure, we can pre-train embeddings using large quantities of unlabeled text. This enables a model to initialize with structured vector representations that can speed up training, improve generalization, and provide a better starting point for downstream tasks. Pre-trained embeddings are often most useful in low-resource settings, in domain adaptation scenarios, or when compute limitations make full end-to-end retraining impractical. However, their effectiveness depends on factors such as how closely the pre-training corpus and vocabulary match the target domain, and whether the embeddings are reused as is, fine-tuned during task-specific training, or remapped to a different tokenization scheme. Potential pitfalls include misaligned vocabularies, bias inherited from the pre-training data, and the risk of degrading useful structure during fine-tuning if it is too aggressive. Pre-training is not always beneficial, but in suitable contexts, it offers a modular and transferable method to incorporate prior distributional knowledge into neural networks. Before pre-training, let us define some key terms. Tokens generally correspond to basic units such as words, subwords, characters, or symbols depending on the chosen tokenization algorithm. Each token is assigned a unique integer index within the vocabulary. For example, the phrase hello might be segmented into 4 tokens: HE, LL, O, and the exclamation symbol. Some tokenizers also append a special end-of-sequence marker after the last token. Once we have integer indices, the embedding layer maps each index to a dense vector in a continuous space. These vectors encode syntactic and semantic information in numeric form. Many modern systems use subword tokenization methods to balance vocabulary size with the ability to represent rare or newly encountered tokens by composing them from smaller units. Effective tokenization and embedding methods are critical because they influence how accurately semantic relationships emerge in the vector space. When embeddings are learned over a representative vocabulary, terms with similar distributional patterns tend to cluster together. For example, vectors for animal concepts like cat and dog correspond closely with each other while remaining distant from tokens relating to water or fire. A vocabulary is a set of token indices designed to match the structure and frequency of a given corpus or domain. When embeddings are trained effectively over this vocabulary, they enable the model to capture meaningful relationships between concepts, often revealing patterns or associations that were never explicitly defined in the data or the model architecture. In static embedding schemes, each token is mapped to a vector independently without considering context or sequence. This approach provides a geometric view of token similarity but ignores the effect of surrounding tokens. Real language understanding often requires context-sensitive representations. By adding transformer layers or other contextual architectures, we generate embeddings that incorporate information from neighboring tokens and syntactic dependencies. These dynamic embeddings yield richer, task-aware representations that reflect how meaning shifts in different contexts. Embedding techniques have evolved far beyond early methods such as word-to-vec, glove, fast text, and BERT. These foundational approaches taught us how to capture syntactic and semantic information through objectives, like predicting nearby tokens, modeling global co-occurrence statistics, and incorporating subword information. More recent work treats embeddings as reusable modules that can transfer knowledge across tasks, domains, and model architectures. For instance, researchers use pre-trained embedding layers from large networks to teach smaller models via distillation. In this process, the student embedding learns to mimic the teacher's vector space or attention patterns, enabling transfer into different embedding dimensions. Other studies analyze how semantic concepts are encoded in subspaces of pre-trained transformers and demonstrate methods to isolate, edit, or transfer those subspaces between models. These developments illustrate a broader trend. Embedding layers have become dynamic components integrated into training workflows, transfer pipelines, and architectural optimizations. However, transferring embeddings across domains or architectures requires addressing vocabulary mismatches and representational differences. Adapting to a new tokenization scheme or reducing dimensionality often necessitates learned projection or alignment functions to preserve the semantic structure encoded in the original embeddings. To pre-train an embedding layer from scratch, start by gathering a corpus that matches the language distribution and terminology of your target application. Then, build a vocabulary by choosing a tokenization method such as word level, subword level, or character level segmentation, and assigning each token a unique integer index. With this vocabulary defined, initialize the embedding matrix randomly and train it using a predictive objective. One common choice is next token prediction within a transformer framework, where the embedding and model parameters are optimized jointly to predict the next token in a sequence. Alternatively, self-supervised tasks like masked token reconstruction or contrastive objectives can be used to train embeddings by encouraging similar tokens to have related vectors and dissimilar tokens to be separated. A frequent architectural pattern is to tie the embedding matrix to the output projection layer in decoder-based models. This approach reduces the number of parameters and enforces consistency by using the same vectors for input lookup and output scoring. After training, evaluate the learned embeddings by testing their performance in downstream tasks. Metrics include clustering cohesion for similar tokens, classification accuracy when embeddings are frozen and used as features, and retrieval quality in semantic search scenarios. In settings with limited labeled data, you can freeze the pre-trained embeddings and fine-tune only a small classifier to assess how well they transfer. Probing experiments that train simple classifiers on frozen embeddings to predict syntactic or morphological features also help measure the linguistic knowledge captured by the vectors. After pre-training embedding layers, they can be used to initialize new network architectures. This typically leads to faster convergence and improved generalization, especially when labeled data is limited. When integrating pre-trained embeddings, there are several strategies available. You can freeze the embedding matrix and only update the higher layers during the training. Alternatively, you can partially fine-tune the embedding parameters to better adapt them to the specific task. If you have access to sufficiently labeled data, you can train the network end-to-end, allowing both the embeddings and higher layers to be refined together. Maintaining a decoupled embedding module that has been trained and validated independently promotes modularity and reuse. This enables the same pre-trained embedding to be plugged into multiple architectures without retraining from scratch. When applying embeddings to a model with a different vocabulary or embedding dimension, mapping functions may be required. For example, a linear projection layer can align vectors from the source embedding space to the target space. If dimensionality reduction is needed, techniques like principal component analysis or learned compression layers can shrink vectors while preserving most of their semantic capacity. These alignment and compression methods allow embeddings to be adapted for smaller models or specialized domains without losing critical structural information. To maximize the benefits of pre-trained embeddings, the embedding layer should be allowed to adapt to downstream objectives during the task-specific training. For example, unfreezing a subset of the embedding weights enables them to adjust to domain-specific language patterns. Choosing an embedding dimension that provides sufficient representational capacity without incurring excessive computational costs helps maintain generalization while avoiding overfitting in low data settings. Higher dimensional embeddings can model finer semantic distinctions, but they increase parameter count at the risk of overfitting. Subword-based tokenization methods should also be used effectively to handle rare or morphologically complex words. By composing rare terms from smaller units, subword segmentation reduces out-of-vocabulary issues and improves coverage. To evaluate what the model has learned, the embedding layer should be examined directly. This can involve visualizing clusters of frequent tokens and inspecting nearest neighbors for selected tokens to assess the consistency of semantic structure. Regularization should be applied to the embedding weights to reduce overfitting, particularly when labeled data is limited. Techniques include dropout on embedding outputs, weight decay on the embedding weights, and normalization constraints. In multilingual or multimodal scenarios, alignment of embeddings across input types should be incorporated. For cross-lingual applications, mapping functions can project embeddings from one language into the vector space of another. In other multimodal contexts, joint optimization can align text and image embeddings within a shared representation space. These alignment strategies support more effective transfer and generalization across tasks and modalities. Pretrained embeddings encode distributional patterns into compact, semantically meaningful vectors that can be reused across tasks, domains, and model architectures. By initializing models with these embeddings, training becomes more data efficient, especially in low-resource or compute-constrained scenarios. Techniques such as projection, alignment, and distillation enable adaptation to new vocabularies, dimensions, or model scales. As neural architectures become more modular and specialized, embedding pretraining continues to serve as a scalable method for transferring prior knowledge and improving generalization across diverse applications. Pretrained embedding layers have become a foundational element of modern neural architecture. When designed and trained deliberately, they bundle semantic and structural priors that enhance learning efficiency and robustness. Whether you're building a language model, a recommendation system, or a multimodal AI, embedding pretraining offers a scalable, transferable way to encode domain-relevant information directly into your models. As models evolve towards smaller sizes and more specialized domains, embeddings will play an increasingly critical role in encoding transferable information. Thank you for your time and attention. This concludes our exploration of pretraining and embedding layer. I encourage further exploration and experimentation with these techniques. For deeper work, consider looking into probing studies, vocabulary transfer protocols, and embedding distillation pipelines.